Alright, I'm breaking down and I'm going to make some videos similar to Organic 2 for your spectra and discussion. So this is experiment number 1, which is the glycine. And I'm going to put my glasses on here, my actual glasses. So there's glycine. In the UV, it's run from 190 out to 400. So for all of your UV spectrum, when you take them, if your compound has actual color, you could run it from 190 all the way to 800 if you want. But the normal UV runs for us is 190, give us that extra 10 nanometers out to 400. So you can see that your final product, right, acetylglycine, what you're looking for is a lump there, the absorption. Now, typically what you see in your UV is a pi to pi star. So your compound normally has to have a pi bond or aromatic ring to see an absorption. If this is really, really concentrated, you would see the peak go really, really high. And normally, if the peak is above 3, it's too concentrated and the top of the peak flattens out. So you can dilute it down, and this is fine, it's down near 1. You can clearly see the absorption is 225. You don't have to, other than writing the structure like on all spectra, you don't have to assign the UVs. This year I ran it in ethanol, but for you folks, you will be running experiment number 1, starting material and product, in water, right? Because it dissolves better. This is the starting material, glycine, right? And you can see the very nice absorption peak goes all the way up almost to 2, right? And then the nanometers on this one is 222. Technically, you have to use the peak picking button on the software to get that number, just like we had here, right? So UVs, there's really not much to it. You just record them, you get a mark for it, and you only discuss it if something really strange shows up in it. Next is the IR. So we'll start with glycine. This is one of the tough things. We don't have good references for amino acids. When you look in other sources, you might see how the nitrogen lone pair acts as a base and deprotonates itself. So this carries a -1 charge because that hydrogen ends up over here, and this gets a positive charge. They call it the Zwitter ion. So it's almost as if in solid structure, if some of it is like this is protonated, but yet some of it might not be protonated. It's the carboxylate anion. This gets a positive charge on it. So not only do you have normal NH2 stretches, but you could have NH3 positive charge types of stretches. So long story short, you get a real mess. So this whole region here, the best you could do is kind of circle it and point at this and say it's your OH carboxylic acid stretch. You could show this deprotonated, the protons here, positive charge, negative here, and say, and or the NH3 plus stretches. It's a mess. This peak, the glycine. So what you're going to see here, 1593, the best you can say is that's that carbonyl. You will also see that NH bending can be quite strong. So this, I would almost circle this right here and say it's either NH bend or the carbonyl stretch of that acid. Other than that, there's nothing else here that is obviously circleable for the glycine. The product, so again, when you're in IRville, you try to only circle what you're pretty darn sure of. So the product looks like this. So one of the things I'm looking at is this nitrogen has an acetyl group on it now. So this NH stretch should be quite pronounced. And it turns out you're going to see one very sharp peak. This one is literally that NH stretch. You have 2 carbonyls. This is not likely to deprotonate this acid group like we just talked about for glycine. Not likely, notice I'm saying. So there's 2 carbonyls. One is an amide, and the amide and carbon-oxygen stretch is usually 1650-ish. This is a carboxylic acid, 17 something. So mine clearly shows a 1719 peak. This one, very, very, very likely to be the carboxylic acid CO stretch. Down here, 2 peaks. One of these is very likely to be the amide carbonyl CO stretch. The other one is NH bend. So I could circle these both and just say, look, one of them is very likely the amide stretch. The other one is the NH bend. That would about do it for that. Nothing else is really significant to circle. And then we move on to the carbon. Let's do carbon 13. So you always label the carbons different by symmetry, and you can see I've labeled this one A, B, C, D. Notice you have two carbonyl carbons. One is an amide, one is an acid. Both are somewhere between 155 and 185. And the numbers for this one, 170, 171, and the carbon, right? See how you see two peaks? I would circle both of these and simply say either carbonyl, B/D. It could be either one. You don't have to discern which one's which. Now, when you run it on ours, what you're going to notice is right here at 40, you see a multiplet. And see on the very side of this multiplet, see this little singlet right here sticking out? That, which is at roughly 41, belongs to this carbon C. This multiplet here, I don't know if it's 5 or 6 little peaks right here, is DMSO, your solvent. When we run it, this little multiplet peak is much lower, closer to the baseline, and you should still see this singlet. It all depends on how concentrated you made your sample, so be careful. Your carbon C is right around here at 41, and it's this one on the side. This one obviously is the methyl group that I've labeled A. This is your proton, and this was run on ours, and you can see here, you could even see way out at 12-ish, see how there's a bump? It showed up. That would be the acid H if it's there, but some of you might not even see this. It might look flat as a pancake, so there's nothing there. You label the different hydrogens, A, B, C, and D. We already talked about D would be here. This is a situation where if you see the hydrogen or nitrogen talking to the next door neighbor carbon's hydrogens, they're coupling. So HB, if it talks to C, you'll see an ugly looking triplet. It might vary a little bit in its location, but in this case, roughly around 8, there's that triplet and it integrates to 1. And on this particular one, you can see roughly a doublet worth 2. That would be the hydrogens right here, C. Hydrogens at A is a singlet. This one right here. And that's at 1.96. We're very close to it. This giant peak for me is water. Now mine happens to be at 2.2, right? Or that's actually, sorry, that's, folks, no. That for me, I ran mine in regular DMSO. So what this means is when I ran it, so I'm just going to finish the last little bit of this video. So basically, I think we already have this assigned. The only thing I was going to add to this was the fact that I ran this on that day in regular DMSO, which means it doesn't have any deuterium on it. So you're going to see a large absorption peak at 2.6-ish. Most of you, when you run this, and you run it in deuterated DMSO, you're going to see a peak of water somewhere out here. So the point is, you're going to see a singlet worth 3 at 1.96, a doublet at almost 4, worth 2, and a little ugly looking triplet around 8-ish. Those are the 3 peaks, A, B, C. The peak D, most of you won't see way out at 12. It's just like a flat line. That does it. So discussion time for the glycine, the acetylation of glycine experiment. So I just wrote down a few things here. You can see the mechanism. This is something that you could find online. Anytime you react acetic anhydride with an amine, it ends up putting the acetyl group on the nitrogen. So the first step is, you can follow that. This arguably, if that positive entity exists for a period of time, it's an intermediate. So that it's an ion that exists in solution for a period of time. So when you make your energy reaction diagram, people would say, why did you put your product organic aceteric acid versus the starting material? Why is it slightly higher? See how they're very close in energy anyway? I just made the argument for qualitative sort of reasons that this has a second carbonyl group, so maybe it's slightly more reactive than the amino acid to start with. Amino acids are not particularly reactive, but I don't care if you put it slightly higher or lower. The interesting thing is, even if this final product was higher than this organic starting material, you might want to say it looks endothermic the way I did it. But that's not true. Your reaction got hot. Acetic anhydride is a very reactive organic functional group compared to this one. So whatever the acetic anhydride does in this overall reaction, whatever part it plays, when it turns into other items and falls down in energy, it gives off more energy than this little bit is needed when all is said and done. So the overall, altogether reaction is exothermic, because one of your observations is it heats up. The other observation is, you know that your starting material and your final product are white crystalline powders. So you start in your flask with a white powder, then all of a sudden, if you're paying attention, it gets warmer, and you'll also see it goes kind of clear. So obviously there's something that has a solubility in the water or aqueous solution you have, which proves this intermediate very likely to be there. And then as it proceeds to make your final product, you get the white solid coming out because it is not soluble in water. So that kind of fits with the mechanism in this reaction diagram. That's fine. You have to talk about, I'm just quickly going through this, the things that you should be talking about, just like last year's organic when I went more at length in it, your yield. Well, obviously most people had a giant water peak in their NMR. So the other thing is, maybe you could let it sit for a week, dry it to get your weight. You could also go ahead and do the NMR by mole correction, which you were shown last year how to do. Right? So you can mention this in your discussion, particularly about the yield. And then the other thing you could do is, once you dry it or do the correction, let's just say you got, I don't know, something like 80%. The other thing you have to talk about is where did all the organic material go? Because the NMR is not showing any leftover starting material that we can see. So one of the things you can do is check the filtrate. When you filter off the crystals, if we could take an HPLC sample of that liquid filtrate against some standards, we could find out where all the organic starting material product went to get a true idea of what the yield is. Doesn't look like there was any decomposition, there was no brown. NMR. You never discuss IRs or NMRs or spectroscopy unless it indicates something to you other than the product. So that might seem strange. So first of all, there's a water peak. We already talked about that in our yield correction. So that just tells us it's wet. The other thing that a lot of them, we don't see clearly that peak over at 12. It should be there. You go to a sign, it's not there. So you can just make a comment that often it's just so broad it doesn't show up. So I think overall, the other observation was the smell of acetic anhydride. So one of the things in this mechanism, when that attacks here and this leaves, that piece ends up showing up at the very end as acetic acid as a byproduct. So your observation of the smell of acetic acid. So the fact is also that if you're smelling the acetic acid, the mechanism says it's there, it's crude. Part of your yield, if you ran an HPLC, maybe even your crude yield would show a little bit of leftover acetic acid on your crystals or in your filtrate. So that'll do it.